Okay, we'll learn about fuzzy sets, its properties and operations on fuzzy sets. Okay, so first of all, what is a fuzzy set? A fuzzy set is an addition to a normal set where you have the degree of membership, something called as degree of membership. Let's take this set right here. This is how you denote a normal mathematical set. Here we have a set A which has values starting with x and going on. What this means is basically the values within this curly braces are present inside the set A. But when it comes to representing fuzzy sets, we have lots of items in the sets, but they are not completely present in the set. These items are partially present in the set, and the degree of the partiality is represented by what is called as degree of membership, and this is a value between 0 to 1. So therefore the value is 1, it means the value is completely present in the set. That is how much the value belongs in a particular set. So this is how you denote a particular value inside a fuzzy set, x by y, where y is the value and x is the degree of membership. You calculate this degree of membership based on a function that is called as the membership function, which basically maps the value to the particular affinity to the set. So this is an overview of fuzzy sets, and let's see what are the operations you can perform in a fuzzy set. In a normal set, you would have seen union, intersection, and complement. We can do basically all that here. Let's take a look at this example here. Here we have two fuzzy sets, fuzzy set A and B, and A has the values A, B, C, and D. Let's make it small so that we don't get confused with this capital A here. So we have A, B, C, D. A is 0.2, that is 20% present in set A. And similarly we have B, which is 0.1, C 0.5, and D 0.7. Similarly we have another set here, set B. So let's say we are performing a union operation on these two sets. So what is basically a union operation? In a normal set, the common values present in both the sets will be present. So here what we do is, in a union, as you can see, we have two common values here. But we don't simply copy these values, you only take the maximum value present in the numerator, which basically means to say whichever set has the maximum participation of the value, we take that. So the resultant will be having A, B, C, D, E and F, and the respective numerators will be 0.2, 0.1. When it comes to C, we have to choose between these two numerators. The maximum is 0.5. So we take that here. For D, the maximum is 0.9. Here 1 and 0. As you can see here, we have E and F. E has 1 as a degree of membership and F has 0, which means to say that E is fully completely present in the set, whereas F is it has the very least amount of association with the set B. Okay, we saw union now. Intersection is basically the same. What we do is we take only the common values between those two sets, and in those common values we take the minimum degree of participation. So the answer for intersection would be the values C and D, but with the degree of membership 0.3 and 0.7, which is the least. Next operation we can perform on a fuzzy set is the complement. Whenever we talk about complement in a normal set, we look at what is the universe set. For example, if let's say this is the universe that we are talking about, and this is a set, normal regular set A. One thing to note is we call regular sets as crisp sets, which basically means to say that the element is either present or not. So in case of crisp sets, the complement of set A would be everything else in the universe other than A. So we do the same for fuzzy sets also. Let's take for example set A, this fuzzy set A and its universe as shown here. Basically for complement what we do is we just subtract the numerator from 1, which means today whatever else is there in the set that is present in the complement. So the complement of fuzzy set A would be small a, which has a participation of 0.8. So small a has a participation of 0.2 in the fuzzy set A and a participation of 0.8 in the complement of A. So same goes to B, which will have 0.9, C which has 0.5, D will be having 0.3, and also all other values present in the universe set carried on. We saw union and intersection, right? These two operations follow all these three basic rules that we used to see in normal sets, that is commutative, associative and distributive. I'll illustrate that here. This is basically equal to, and you can replace this with intersection as well. Associative is you can compute whichever set first you want, the result will be same. Basically, the algorithm that we use use as reduce operations in programming, right? So basically, you can reduce in whichever order you want, the answer will be the same. Third one is distributive. Here the operations would be the same all over. So if it is union, it should be union all over. In that case only you can do in whichever order you want. So this is distribution. So let's look at associative in detail. Associative rule basically means you can bracket this in any order, in any group you want, and the result would still be the same. In case of distributive, we have one operation here and another operation inside. So we can distribute union over intersection in this case, and the result is equivalent to you can replace union with intersection here and still if the rule holds. So a small recap of what we saw. We saw what is a fuzzy set, we compared it with a normal crisp set, and we looked at what is degree of membership and what it means for a value to be present inside a fuzzy set. We also looked at several operations that we can perform on a fuzzy set. We saw the rules it follows basically. We'll look at a few examples for the rules that we are seeing here. One thing I see here is that they have made an error here. This should be C. The set C. And we'll have an example for each of this. We'll see the example of distributive alone. We should basically cover everything else. Let's take fuzzy set C. Perform that on this statement here. We'll take the images first. Since we are having brackets here, we'll perform B intersection C first. As you can see, the intersection between those is actually the null set. So we have A union null set for LHS.
Yes.
Small f capital. One doubt you can have is this is smaller, this is capital, so they are actually different elements. A union the null set will be nothing but the A set itself. Let's take the RHS. A union B set. A union B set will have A, B, C. And then we'll have to find A union C. One thing you can note here is for both the sets A and C, we have the membership of B same. So that for union we take the maximum. In this case, both are 0.1. Now we are performing intersection on both of these. The intersection would be since we are taking intersection for D, we take the minimum value over here, which is 0.7. One thing you can see is we had the LHS as the set A. This is nothing but the set A. So therefore, we can say distributive law is not true. So similarly, we can prove commutative and associative also. Basically, the same which same holds for regular sets also.